This presentation will cover the Diels Alder reaction by looking at the mechanism and the effects of the stereospecificity in the dienophile. Let's start by discussing the mechanism. There's four main components that we all need to remember when talking about the mechanism of the Diels Alder reaction. 3 pi bonds are broken in order to form 2 new sigma bonds, which are located there, and a new pi bond. This reaction is always initiated by heat. The product is always going to be a 6-membered ring, and this reaction is always concerted. So just to show you where all of these broken bonds end up going, the electron pair will push off one of the double bonds in the diene, attacking the alkene of the dienophile, which will push this electron pair off to attack the other double bond of the diene, and then this electron pair will push off to form the new pi bond. And we did color code the diene and dienophile double bonds so that you could follow which pi bonds were broken in order to form which of the new bonds. Okay, so now let's take a look at how to draw the mechanism and product of a Diels Alder reaction. Our first step is going to be to rotate our diene about its sigma bond in order to make sure that it is in the S-cis conformation. Step 2 will be to place our dienophile with its double bond as close as possible to the diene. Next, we're going to draw our arrows to show what bonds are being broken and what new bonds are being formed. Being very careful exactly where we point them. And then finally, we are going to draw our product, which just has all of our new bonds drawn in. And the one thing we want to be careful about is what Abia is about to discuss further with you, which is that the stereochemistry of the dienophile is retained in the final product.
Now we'll look at stereospecificity in a Diels Alder reaction. So in our first example here, we have a reaction with a cis dienophile. This means that the substituent groups in the dienophile are on the same side. Because they're on the same side in the reactants, they end up on the same side in the products. And because you could have either this product or this product, both of these products are the same and are called meso or identical products. On the other hand, when you have a trans dienophile, this means that the substituent groups are on opposing sides and you get 2 enantiomers with trans groups on opposing sides. So one basic rule to follow with stereospecificity is that the stereochemistry of the dienophile is retained in the product. This means that a cis dienophile yields a single achiral meso or identical compound, and a trans dienophile yields 2 enantiomers with trans groups.
Now we're going to talk about the retrosynthetic analysis of Diels Alder reactions. And what it is, it's just the reverse of Diels reaction. So in this case, we start with the product, and then we end with the diene and dienophile. And I just wanted to point out that the 2 lines with the arrow means that the reaction is going in reverse. Now I'm going to explain some of the rules or tips for solving these problems. The first thing we need to do is find the 6-member ring with the alkene. So here is the 6-member ring with an alkene. And then we have to draw in the 3 arrows to reverse the reaction. So when we are forming Diels reactions, we are breaking 3 pi bonds and then forming 1 pi bond and 2 sigma bonds. However, when we're reversing the reaction, that means we need to break 1 pi bond and 2 sigma bonds and then reform 3 pi bonds. So in this reaction, we are showing the arrows. We're breaking 1 pi bond here, 1 sigma bond here, 1 sigma bond here. And then we are reforming the diene and dienophile. So here's 1 pi bond, 1 pi bond, 1 pi bond. So these are the 3 pi bonds we just reformed. And it is always important to remember stereochemistry when doing these reactions, and I will explain more in the next slide. Now I'm going to show you some examples of how to do these reactions. So in the first example here, we have the 6-member ring with the alkene, and then we need to draw in the arrows. So we have one pi bond breaking, one sigma bond breaking, one sigma bond breaking, and then we have one pi bond forming, one pi bond forming, one pi bond forming. And then in this case, it's a little bit different because now we are showing the stereochemistry. So these two are on the same side. In the end, you have to have the product has to be on the same side. And then the next one is kind of the same thing. You're doing the same arrows, and then we have the same product. And the reason why we have the same product is because there's symmetry between these 6-member rings. Now the last example, we have the stereochemistry just a little bit different because we have the two going in opposite directions. So in the end, your product needs to have the lines going in opposite ways.